and welcome back to our video series on inference. In the last several videos, we have looked at calculating confidence intervals and doing hypothesis tests for proportions and for means when we had known population standard deviation. And in our last video, we looked at the t-distribution and how to calculate probabilities and find critical t-values when we're dealing with the t-distribution. In this video, we'd like to look at calculating confidence intervals and doing hypothesis tests for means when we have unknown population standard deviation. Now, we need to recall with unknown population standard deviation, we have to use a t-distribution. And t is defined as x bar minus mu 0 over s over the square root of n, where s is our sample standard deviation. And this is distributed as a t with n minus 1 degrees of freedom. Well, if I'd like to create a confidence interval, I need to solve for mu 0. Well, if I do just a little bit of manipulation on this, I can find that by multiplying by s over the square root of n to both sides, and then solving and getting mu 0 by itself, I get x bar plus or minus my t with its degrees of freedom over s over the square root of n. Now, as an example, suppose I'd like to create a 98% estimate of the mean age of employees at a local call center. Now, perhaps I know there are 100 employees at the call center, but talking all 100 is too expensive, and so I plan to take a sample. And the first thing I need to know is how many do I need? Well, I need to first look at what does my distribution of these ages look like. So for all 100 individuals, my distribution, my histogram of these ages, appears to be slightly skewed to the right. So it's definitely not normally distributed. And so I know that I'm going to have to invoke the central limit theorem. And the question is, do I need a sample of size 15 or more or a sample of size 40 or more? Well, when I look at my box plot of these ages, I see that there are no obvious outliers. There are no outliers at all. And so this is going to allow us to say, well, we can use 15 or more, and the central limit theorem will be applied. So suppose we take a sample of 16 employees, but we don't know the population standard deviation. Again, we've got to use the t-distribution. And so our confidence interval formula is x bar plus or minus our t with its degrees of freedom times s over the square root of n. Well, the degrees of freedom, remember, are n minus 1, and so I'm going to have 15 degrees of freedom here. Suppose these are our ages. Now, the sample mean for these ages is 39.8425. The sample standard deviation, 4.974994. N is 16. And the t-value for 98% confidence with 15 degrees of freedom is 2.602. Then, plugging in the information we have for our confidence interval, we see that we've got 39.8425 plus or minus 2.602 times 4.974994 over the square root of 16. Now again, x bar is my point estimate. This t with its degrees of freedom times s over the square root of n gives me my margin of error. And so what I come up with is 36.60627 to 43.07873. And to interpret this, we're 98% confident the mean age of all employees at this call center is between 36.61 and 43.08 years. But suppose instead we'd like to take this same sample and determine if the mean age is less than 42. Then our null hypothesis, mu is greater than or equal to 42. Our alternative hypothesis, mu less than 42. And let's suppose we're going to use an alpha of 0.01. Well, again, x bar minus mu 0 over s over the square root of n is distributed as the t with n minus 1 degrees of freedom. Our x bar value, 39.8425. Our mu 0 value, 42. Our sample standard deviation, 4.974994. Our sample size is 16. That's distributed as a t with 15 degrees of freedom. And when we do the arithmetic, we find that we get a t-value of negative 1.735. Now, the probability of t with 15 degrees of freedom less than negative 1.735 is the same as the probability of t with 15 degrees of freedom is greater than 1.735, and that is 0.0516. But remember, alpha is 0.01. And so our decision is to fail to reject because p is greater than alpha. Therefore, there is insufficient evidence to conclude the mean age of all call center employees is less than 42. This is our conclusion. Recall, our decision is based around the null. Fail to reject the null. However, our conclusion is based around the alternative. There's insufficient evidence to conclude the mean age of all call centers is less than 42. Decision based around the null, conclusion based around the alternative. Okay, so how might we do this in R? Well, let's take a look. Okay, so here are my ages. I've just called them X1, and I'll run this. Now, if I do a histogram of just these values, what I'll see is that these look relatively uniform. And if I do a box plot of just these values, I see that, well, there's no outliers here at all. X bar, that's the mean of X1. That's what I've defined that to be. SDX1 is the standard deviation of X1. And so we can go through and run these. QT with 0.99 and 15 degrees of freedom, lower tail equal true. This gives me my T star value. I've used 0.99 here because I need 0.01 above and I need 0.01 below. And so I know that if I have 0.99 below, that means 0.01 is above. And so that's going to give me my critical T value. And this is going to be 2.60248. Now my confidence limit, my lower confidence limit value, X bar minus my T star times S over the square root of N. I can run this. And my upper confidence value, X bar plus my T star times S over the square root of N. I can run this. And what I get is my lower confidence value here, 36.60627. My upper confidence value, 43.07873. And we're 98% confident the true mean age of all employees at this call center is between 36.61 and 43.08 years of age. This is the long way. However, I could just use the t.test function. I plug in my x1 values. Here I'm using an alternative equals 2-sided. If you're going to find a confidence interval, you need 2-sided, so it'll give you both interval values. Here's my mean, 42. Here's my confidence level, 0.98. And if I run this, notice what I get, 98% confidence interval, 36.60567, 43.07933, 36.60627, so just a little bit off, 43.07873, just a little bit off, because we have rounded our confidence level value here. Okay, so what about our hypothesis test? Well, remember we said mu0 was 42. We're using the same X bar and standard deviation and sample size, so I'll go ahead and run these three. Now my T value here, X bar minus mu0 over S over the square root of N, and I get a T value of negative 1.734675. This PT function gives me my probability. Remember, I'm doing lower tail because I have less than here in the alternative. So I want lower tail equals true. So the probability of my T, this gives me my T value. I have my degrees of freedom at 15. And if I run this, I get 0.05164644. However, this is the long way. This is just using the function t.test. Again, my x1 values. Here I've got alternative equals less, and I've got my mu equals 42. So let's see what this gives us. Well, notice I get my t value, negative 1.7347. I get my degrees of freedom, 15. And I get a p-value, 0.05165. Well, let's take a look and see. My t value I got the long way, negative 1.734675, negative 1.7347, so just rounded. My p-value when I did it the long way, 0.05164644, 0.05165. Also notice what happens. When I have a less, notice what happened in my interval. Negative infinity is always going to be less. And so if I'm trying to create a confidence interval, I cannot use less or greater. Hence the reason I mentioned two-sided in the confidence interval portion of this. Okay, that's it for this video. In the next video, we will begin looking at paired data. See you then.